You can write flawless, fully tested code on your local machine and still deploy a system that is entirely compromised. Modern applications are rarely built from scratch. Developers rely on package managers to automatically pull in hundreds of external third-party libraries to handle routine functions. Because of this architecture, an attacker rarely targets your proprietary code directly. Instead, they hide a malicious payload deep within an obscure nested library that your application depends on. As this terminal shows, accepting serialized data from an untrusted client without rigorous integrity checks can be catastrophic. An insecure deserialization vulnerability triggers remote code execution, granting immediate root access to the system. Importing an external component without strict verification bypasses your local security controls. You are importing that component's entire attack surface directly into your core product. Defending the software supply chain requires addressing two overlapping security standards: OWASP Top 10's A08 for software and data integrity failures, and Proactive Control C6 for keeping components secure. This diagram illustrates a compromised pipeline. Here, an unhardened CI/CD system pulls code from an untrusted repository, injecting a malicious package into the build phase. Secondly, vulnerable dependencies. Notice how this approved component decays. Attackers constantly scan for and exploit these outdated libraries. The third vector involves unverified updates. When an application or an IoT device downloads automated patches without checking cryptographic signatures, attackers hijack that update mechanism to distribute malware at scale. Every one of these attack vectors exploits the exact same architectural flaw. The system relies on implicit trust instead of verifiable cryptographic proof. To correct this, we implement phase 1 of our defense model, the gatekeeper. This is an absolute perimeter boundary enforcing strict ingestion rules so that no unvetted library enters the codebase. The first pass requires subjective evaluation. An engineering team must evaluate a new project's popularity and look for verifiable maturity within its open-source community. We actively avoid highly complex early-stage projects. Instead, we select components that demonstrate a clear, documented history of active and responsive maintenance. Establishing this rigid vetting perimeter acts as a critical first filter. It drastically reduces the statistical probability of adopting inherently flawed software before a single line of code is imported. Subjective vetting is a starting point, but it is insufficient on its own. It must be paired with objective cryptographic verification of data provenance. A digital signature acts as a mathematical lock, guaranteeing the package wasn't tampered with. Engineers execute a check using tools like cosign. The system validates the key, confirms the signature, and allows the package to pass safely through the perimeter. If that signature check fails, the automated protocol must trigger immediately. The build process halts, and the asset is quarantined for manual review. Enforcing digital signatures removes human assumption from the equation. Trust becomes a mathematically verifiable engineering artifact. Even with digital signatures in place, allowing development environments to pull packages directly from open internet package managers exposes the organization to unnecessary risk. This routing diagram compares a highly vulnerable direct connection to the public internet against a secure, isolated route passing through an internal, vetted proxy repository. High-risk environments utilize tools like Harbor to host and manage these secure proxy repositories, turning them into isolated, known good caches for the engineering team. As the final step before any package is committed to the main branch, the pipeline executes a localized software composition analysis, or SCA scan, to detect known code flaws. Combining rigid selection criteria, cryptographic signatures, internal proxy vaults, and localized SCA scanning creates a comprehensive gatekeeper. The ingestion attack surface is effectively sealed. Securing the perimeter is only half of the architecture. As this pillar demonstrates, structural integrity degrades over time. A perfectly secure library accepted into your codebase today inevitably becomes a critical vulnerability tomorrow. This requires phase 2, the watchtower. We must implement continuous automated maintenance of the internal ecosystem. The foundational rule of internal security is absolute. An organization cannot protect, monitor, or patch an inventory that it has not thoroughly cataloged. This visual shows a compiled application splitting to reveal internal components mapping directly into a hierarchical software bill of materials, or SBOM. The build node dynamically exports this SBOM as a standalone artifact alongside the binary at every build. Once generated, the SBOM contents must be continuously cross-referenced against active threat intelligence databases. The primary external source for this intelligence is the National Vulnerability Database, tracking all newly published common vulnerabilities and exposures. This is an OWASP dependency track dashboard. By feeding the SEOM into continuous monitoring tools like this, the system automatically detects a match with a new high-severity CVE alert the moment it is published. Detecting the vulnerability is only the first step. Relying on a slow, manual patching process creates an operational bottleneck that attackers will immediately exploit. We eliminate this bottleneck with tools like Renovate. The moment a patch is available, the tool automatically generates a pull request to bump the dependency version. Coupling continuous SBOM scanning with automated pull requests removes the friction from patching. The development lifecycle shifts from a reactive scramble to a proactive, automated process. Finally, we must look at the environment executing these controls. The CI/CD pipeline itself must be just as secure as the code it evaluates. Locking down the pipeline requires strict network segregation and rigid role-based access control to limit who modifies build environments. We enforce routine configuration reviews to ensure the pipeline environment does not drift out of compliance over time. Looking at the pipeline from a macro level, we see the complete defense model. On the left, the cryptographic gate controls ingestion. On the right, the SBOM generator and automated loops handle maintenance. An assumed reputation will never be enough to secure a software supply chain. Mathematical proof and constant vigilance internally are mandatory requirements. Remember, trust is not a security control. Verify every import, catalog every component, and automate your defenses to shut down supply chain attacks before they ever begin.